So this is an evaluative task on water crystallisation from OCR 2011. We've got a student carrying out an investigation where they're trying to find out the number of moles of water associated with sodium bromide when it is hydrated. So here we've got the hydrated sodium bromide. We're then heating it up to evaporate off the water, and we're left with the sodium bromide in the crucible, and the water's gone out into the atmosphere. The first part is to complete the table. Straightforward subtraction. So if we want to know the mass of the contents after heating, we have to take the mass of the crucible and the contents after heating and deduct the mass of the empty crucible. And then if we want to know the mass of water removed, we have to look at the mass of the contents before heating and take away the mass of the contents after heating. Everything else is whatever has gone off into the atmosphere. The first two calculations are reasonably straightforward. We use N equals M over M, so moles equals mass divided by molar mass. The mass of the water taken from here, 18 from the periodic table, and then the mass of the anhydrous from here, and divide through by the mass of sodium bromide. Again, that might vary slightly depending on which periodic table values you're using and which periodic table. So then we've got our two values for numbers of moles. The next one is use your answers to 1 and 2 to calculate the value of X. So the thing that we need to recognise here is that we now have a ratio. For every 0.0544 moles of water, we have 0.0244 moles of sodium bromide. In order to make this a simple ratio of whole numbers, divide through by the smallest, which is this one here, to give us 1 for the sodium bromide, and if we divide through by the smallest again, we end up with 2.25, 2.26, depending on what values you've got here from what values you've used here. So you might have slight discrepancy between 2.26 or 2.25. From there, we then move on to a calculation of error. Now here what we're taking is the uncertainty that we have got in the apparatus, 0.005, and we're dividing through by the mass of the contents before heating, which we are taking from the table just here. Oh, that should be 3.47, not 3.49, and multiplying that by 100, which gives us 0.14. The thing that here we have to recognise is that to make a mass measurement, so to get this mass measurement here, we are going to have taken two readings. So this value here is process data, and to get this we took a reading for the crucible and a reading for the mass. Therefore we've taken two mass readings, and so we would multiply our 0.14 plus its other numbers by 2, which gives us 0.29. Now I just want to point out here that even if you quote your answer to 2 sig fig or to 3 sig fig, when you are then processing this number further, you must make sure that you use the whole calculator value. If we multiply this by 2, we get 0.28, but obviously if we're using the full calculator value, then we end up with 0.29. And these things matter as you process onto more complex calculations with a number of steps. Now you could argue against this being the actual final percentage, because what we're measuring is actually the crucible and the contents. We could therefore say that the error looks at both the mass of the contents and the mass of the crucible, and so the actual percentage error is smaller than the 0.29 which we've measured, but the procedure here is to do the error divided by the mass that we're actually measuring, and then if we're taking two measurements, to introduce a factor, multiply it through by 2. And as I said, this here should be a 7, not a 9. The next question is a little bit more complex. It requires a little bit more thinking. The anhydrous sodium bromide had absorbed water from the air while it was cooling and before it had been reweighed. So you've heated it up, you've evaporated off your water, and then while you're waiting before you reweigh it, it's absorbing some water from the air. So the apparent mass of water that's removed is going to be less, because when you put the crucible back onto the balance, the mass of the contents after heating is going to appear to be greater. Therefore, the difference between that and the mass prior to heating will actually be less. So if we think about this in terms of the number of moles of sodium bromide that we have will appear to be greater, because our mass is going to appear to be greater, and the number of moles of water will appear to be less. then X will actually reduce. Now, in terms of this, for myself, I have to think about this in numbers. I have to use real numbers. So originally we said that if we take the water and we divide that through by the moles of NaBr, so this is just what we did here at the very beginning, so the number of moles of water divided by the number of moles of NaBr, which gave us our 2.25. If we're in a situation like we are in error number 1 here, where we are increasing the NaBr apparent and decreasing the water apparent, I prefer to put in real numbers. So if the NaBr is increasing and the water is decreasing, then I increase my NaBr value, doesn't matter by how much, and I decrease my water value, again, it doesn't matter by how much, and I look at what that number is in comparison to the original. So for me, in terms of processing, I have to interact with real numbers. That's the way that my brain works. Yours might not need to do that. But by inputting these new numbers, I get 1.3, and that tells me that the value of X will decrease. So the value of X here goes down. Then if we have error 2, carbon from the Bunsen flame was deposited on the crucible when it was heated, so that would be due to incomplete combustion. The apparent mass of water removed again is going to be less because of the mass of the contents after heating will appear to be greater. The carbon will add mass when we're reweighing that crucible. So again, we will have an appearance that the number of moles of NaBr will increase, an appearance that the number of moles of water will decrease, and using this same method, the value of X will go down. The next two errors, the crucible supplied for the experiment had not been cleaned properly and had some traces of calcium carbonate powder on it, which we wouldn't be aware of until afterwards. The thing here is that when you are heating it, calcium carbonate will decompose into calcium oxide and carbon dioxide. So we're actually producing a greater volume of gas. This means that we are going to have our water is going to appear to be greater. And our NaBr, we could suggest that would remain the same, or it could decrease depending on how you look at the decomposition and how you treat the initial mass. With this one here, some of the sodium bromide crystals jumped out of the crucible during heating. So here, if we have got a greater loss of mass because some of the crystals are being removed, we assume that that loss in mass is due to water. Therefore, we've got more water appears to have been lost, even though it isn't really. This means again that our number of moles of sodium bromide apparent will decrease and our number of moles of water apparent will increase. Using the method from earlier, if we input real numbers and we alter the sodium bromide on the bottom going down and the water on the top going up, we'll now have a number of 3.5. Again, these numbers are completely made up. As long as it's greater than the one it was up here and smaller than the one it was up here for the sodium bromide, it doesn't matter. This number isn't a real number. The only thing we're taking from this is what is this number in comparison to the original. So on this one, the value for X would increase. So for both of these where we've got increases in water apparent, the value of X would increase. The last question is suggesting improvements. Now if we look at this, these are our errors. So use this as your starting point. If these are the errors, what could the improvements be? Now the thing that you have to notice here is it says assume that the apparatus supplied was clean. So that means that realistically this error here we can't discuss because the solution to that, the improvement to that would be to clean the apparatus. Now the answers for this one are here, are just here. So we've got improvement number 1 is to use a lid to stop spitting, and that would connect into this one here. So if we've got a lid, they can't jump out. Improvement number 2, heat to a constant mass to ensure complete dehydration and to ensure that all water has been removed, because there is a possibility that some water might not have been removed. The next one, heat with a gentle flame or a controlled temperature. Now this would avoid decomposition of the product because it is possible that anything that you are heating can decompose thermally if you apply enough heat. The other explanation for this one could be, and this doesn't relate to cleanliness, so this would be okay, carbon from the Bunsen burner flame was deposited while it was being heated. So in this, you would want to make sure that you are constantly heating, but you are either using if you're using a yellow flame, you are going to get carbon deposited, so you might want a hotter flame, but to keep that hotter flame further away from the apparatus. So you're heating on a hotter flame, but from a greater distance. Improvement number 4. Use a larger mass of crystals. If we're using a larger mass, then that would mean that our percentage errors are reduced. Use a desiccator to cool and dry. Now this would be connected to this one here, prevent absorption of water from the atmosphere. So use a desiccator or cool it in a very dry atmosphere. Stop moisture being absorbed. Repeat the experiment is usually quite a vague improvement. It's not always credited with marks in IB and A-level examinations, so it is something that I would restrict to using unless it's the only thing that you can think of as an improvement, and use a more accurate balance, which kind of links in with the this improvement here. It's a similar sort of thing in that we are trying to reduce the percentage error. So a more accurate balance, one that has got a greater number of decimal places on it, would help also to reduce the percentage error because there would be less uncertainty involved in that.